Linear programming. In this video, we'll solve a real-world problem that has constraints by setting up an algebraic system of linear inequalities. Constraints are boundaries or restrictions in a problem represented by linear inequalities. Objective function. It's the function to be maximized or minimized. Linear programming is the process of maximizing or minimizing a linear objective function, subject to constraints that are linear inequalities. And the feasible region, also known as bounded region, are all of the points in the intersection of the graphs of the constraints. So we'll look at our first maximum and minimum value problem. Here we're given a feasible region which has already been designed. The vertices of this region are A, B, and C. And we're asked to find the maximum and minimum value of the objective function, which has been given as C equals 2x plus 7y. So we'll start with identifying A, B, and C. Those are the vertices of the feasible region. Coordinates of point A are -3, 2, B, 2, 5, C, -1, -3. Now we'll use the objective function. C usually stands for cost, equals 2x plus 7y. And if I substitute -3 in place of x and 2 in place of y, the value of C is 8. For point B, the value of C is 39. And for point C, the value of the function is -23. So we'll have our first word problem now about hats and scarves. Kim wants to knit and sell hats and scarves. A hat uses 6 ounces of yarn. A scarf uses 9 ounces. Kim has 72 ounces of yarn, and she wants to make at least 3 hats. The profit on a hat is $10, and the profit on a scarf is $20. So how many hats and scarves should Kim make to maximize her profits? This is a perfect word problem to set up and solve using linear programming, because there's several constraints. We're talking about hats and scarves, so when we assign our variables, let x equal hats and y equal the number of scarves that Kim knits. Now in our constraints, we know that the hat uses 6 ounces of yarn, the scarf uses 9 ounces, but Kim has only 72 ounces of yarn. So that's why we're going to use less than or equal to 72. We know she wants to make at least 3 hats, so x has to be greater than or equal to 3. We know that she'll make at least 0 scarves, right? She's not going to make a negative number of scarves. And what we're going to do is take those inequalities we just wrote, we'll graph them, and we'll solve the system. We'll write an objective function, which will be the profit function. So P equals 10 times x plus 20 times y, representing the profit she makes from x hats and y scarves. And then once we graph and solve the system of inequalities, we'll determine the x, y that optimizes the function. So we'll get some practice with this problem. And remember, x was the number of hats Kim knits. She wants to make at least 3 hats. Y is the number of scarves she knits, and she'll make 0 or more scarves. The yarn requires 6 ounces for hats and 9 ounces for scarves. Remember, she has up to 72 ounces of yarn, and we can write that in slope-intercept form as -2/3 x plus 8. And the profit, now remember, she makes $10 for each hat and $20 for each scarf. So now let's graph our system of inequalities. We'll start with x equals 3. Now x is greater than 3 is everything to the right of that blue line, right? y equals 0, and because we're talking about y is greater than or equal to 0, it's everything above that x-axis. And now the y equals negative 2/3 x plus 8. There's my y-intercept. Let's use our slope, and we'll graph that line. And because we want everything less than or equal to that, it's everything underneath that slanted line. So we're talking about the region that's bounded by these 3 points. It's everything inside there. And so we can identify our coordinates of our vertices as A, B, and C. And we can write down those coordinates. And now we're going to use those coordinates to determine the maximum profit that Kim can make if she knits and sells hats and scarves. And what we did was we substituted the x and the y into the profit function. You can notice that 150 is the most amount of profit she can make. So she should knit and sell 3 hats and 6 scarves to maximize her profits. So now I have a problem that you can try to solve. It's called Henry the Woodworker. Henry makes toy cars and trucks out of wood. It takes him 2 hours to make a car and 4 hours to make a truck. He makes a profit of $8 for each car sold and $18 for each truck sold. This week, Henry wants to make at least 6 toy cars. So there's one constraint already. He has at most 60 hours available. There's another constraint that we can turn into an inequality. How many of each should he make in order to maximize his profit? So I'll get you started, but then I think you can put it on pause and keep going on your own. You can come back and check. So to get started, let's let x equal the number of cars that Henry makes and y the number of trucks that he makes. So I'm going to ask that you represent your constraints. So what do you know about x? He wants to make at least 6 cars. And he only has 60 hours this week. So hopefully you'll agree this set of constraints represents the problem. Now you're going to graph the inequalities, right, on some graph paper. Don't forget your objective function, which is going to be about profit. P equals 8 times x, right, plus 18 times y. So go ahead and graph your system of inequalities, identify the coordinates of your bounded or your feasible region, and see if you can identify how many cars, how many trucks Henry should make to maximize his profit. So this is what we came up with for the constraints and the graph. And he makes the most amount of profit by making and selling 6 toy cars and 3 toy trucks.